So here we have drawn a part of the recursive call tree that the algorithm will execute for the example that we had before. So we'd start with a max profit of 10, and max profit of 10 in return would require us to compute max profit of 9, which is what happens if we decide to ignore 10. Or if we include 10, then we have to exclude 9, 8 and 7, all of which overlap, so we have to compute 6. In the same way, 9 will generate 8 and 3, 6 will generate 5 and 4 and so on. Now the point to note is that here, for instance, we need to compute max profit of 5, but we also need to compute it here. And so if we do it recursively, it will compute it both when it's called under 8 and also when called under 5. In the same way, we need to compute max profit of 3 here, here, here and here. And in the same way, we need to compute max profit of 4 here and here. So the point is that the naive recursive evaluation of this function will result in the same subproblem being solved multiple times, and this is what we want to avoid. So how many problems are there? Well, it's easy to see in this particular case that we only have problems of the form 1 to I for I from 1 to 10, right? So therefore there are actually only in general n subproblems if we have n tasks, right? And the problem with the recursive formulation is that we may reevaluate several of these, and in the process we end up in general computing an exponential number of subproblems, right? And this is what we want to avoid. So to avoid this re-evaluation, okay, what we will do is we will store and look up computed values. So the strategy is to store each computed value in a table, okay? And what you do is you look up the table before making a recursive call. So before you recompute, before you make an explicit recursive call, you first see if the value is available in your table. Okay? So this table is usually called a memo table, and this strategy, which evaluates every value of every subproblem exactly once and then stores it in a table and looks it up, is therefore called memoization. So here is the same recursive function written to use a table. So as before, in the base case, we can just directly return the profit 1. On the other hand, if it is not the base case, we compute j as before, which is the last job that ends before job n begins. And now we know that we are going to need the values n-1 and j. So we look up this table, which we are calling max profit table, and we see if the entry for n-1 has been computed before. If it has not been computed before, we compute it explicitly by calling the recursively the same function. Similarly, if the value for j has not been computed already, we call it recursively and compute it and store it in the table. Now we reach a stage where we know that these two values have been computed, so we can now directly return the maximum of this table value or the profit at n plus this table value. And in future iterations of this recursive call, we will never call the same argument again, because before we call it, we check if it is defined, and as soon as we compute it the first time, we store it in the table. Okay, so this is the memo table here that's being used, and notice that we use the square brackets to indicate that these are arrays. So this is basically an array with entries 1 to n, and this array is filled up each time we evaluate the function for that particular argument the first time and only once. So it turns out that we can actually do a further improvement. So what we can do is we can analyze the dependency of entries in the table, right? So here we know that if we are computing, for instance, the table entry at some particular I, then it only depends on values to the left. It depends on some I-1 and some value j, right? So if we can actually iteratively compute these entries from left to right, then whenever we fill up an entry, we know that the values it depends on have already been filled up. And so we can actually replace the memo table algorithm with a recursive function call by an iterative algorithm which computes exactly the same table but from 1 to n. So here is the iterative version of the memo table algorithm. We initialize the table entry 1 to be the profit at 1. Now for 2 to n, as before, we compute j to be the last job that ends before job I begins. And we now can directly assume that max profit table of I minus 1 and max profit table of j exist because they are of smaller values and they have been already computed in this loop. So we can directly compute max profit table of I as the maximum of these two quantities and update the table entry at I. And at the end of this loop, we just have to return the max profit table entry at n. So in this version, it is immediately clear that the loop occurs n times. So we have on iterations of the loop. Now it appears as though this step is a linear scan. That is, we have to keep checking the last job that ends before I. So we have to start from 1 and go up until we find the last job. But actually, since we have sorted the jobs in ascending order of the finish time, it turns out that the next value of j for larger I will be bigger than the previous value of j. So in fact, j only keeps monotonically increasing. So within each iteration of the loop, we just have to keep walking forward, and overall across all iterations of the loop, we only do one scan from 1 to n to fix the value of j. So it is overall a linear algorithm for this problem, even though we are using a recursive formulation and we are in some sense explicitly computing every possible subproblem. Of course, this is linear, assuming the problem has been sorted in advance. So we also need to think of the fact that we need O n log n time to sort. So if the input was not already sorted by finish time, we have an n log n step to sort by finish time. And having done that, even though we explicitly evaluate every possibility, we are able to efficiently compute this in linear time. So it's worthwhile to comment on the difference between the recursive memo table version versus the iterative one. So the advantage of the recursive memo table is it only computes values as needed. In some situations, there may be some subproblems which are never actually reachable from the original problem. And in such situations, you would not need to compute those values at all. So the recursive memo table is more optimal in terms of which entries it computes. On the other hand, this will blindly compute, if you do it iteratively, blindly compute all table entries. So there is some wasted effort potentially. On the other hand, it is a fact that recursion is expensive. This is because in any programming language, if you make a recursive call, what you have to do is you have to save the state of the current function onto the stack, and we have to place a new stack pointer, a new stack frame, and so on. So this bureaucracy of dealing with recursion at the level of implementation of programming language makes recursion much more expensive than iteration. So iteration is cheap. And ultimately, iteration is what wins out. So usually it is much better, even at the cost of wastefully computing some table entries, to compute them iteratively in some fixed order rather than rely on recursion to compute an optimal subset of table entries. So actually, now coming to what we started with, this version, the iterative version, is what, if you look at modern algorithm terminology, is called dynamic programming. Right? So this is what we really mean when we say dynamic programming. It means that we come up with a way of cleverly organizing our subproblems so that we can record their solutions in a table and fill up this table in an iterative manner. It is also important to recognize the gain of organization. Right? So it is not a trivial fact that we sorted the input in terms of finish job time. Because if we did not, we would have, as we had said earlier, we would have to exhaustively check all subsets. And as we know, all subsets of a set of n items would be an exponential number. There will be 2 to the n such subsets. Now here, after sorting, okay, we only have subsets, as we already observed, of the form 1 to I. So we have n subsets. So in particular, we don't need to look at subsets of the form, say, 1, 2, 5 or 3, 8. right? So these kind of subsets never need to be considered, and even though we don't consider it, the beauty of the dynamic programming approach is that we have implicitly covered all these because they are part of the problems that we have covered. So in a sense, we reorganize our original problems so that the sub-problems are well structured, and we have a manageable number of them, such that solving this manageable number of sub-problems actually exhaustively covers all possibilities for the original problem. Let us recap the main points that we have seen in dynamic programming. So the first point is that we are always exploiting the principle of optimality. We are trying to decompose a problem we have into sub-problems and combine the solutions to these sub-problems to solve the original problem. Now the difficulty is that these sub-problems may not be disjoint, they may overlap. So we can't use divide and conquer as a strategy to break up the problem and solve them recursively. Similarly, there may be no predefined strategy that always works in order to discard some choices of sub-problems, so we can't apply a greedy approach. So therefore, we are left with no option but to try all possible combinations of sub-problems, but this may be exponential. So we try to identify a suitable ordering on our original problem so that we reorganize the sub-problems to come down from an exponential number to a polynomial number. We now use a recursive solution, but in the recursive solution, if we do it naively, we might wastefully recompute values again and again. So we use a memo table to remember values. Once we have computed a value once, we only have to look it up in future calls. Instead of using recursion, we can now fill up this table iteratively if we analyze dependency and ensure that we insert a value into the table only when all the values that it depends on have already been inserted. And this can usually be done quite easily by looking at the recursive formulation of the problem. So in this unit, we will see several other examples of problems which can be solved efficiently using dynamic programming. But before we conclude this introduction, let's just look at some historical background. So this technique of solving problems by looking at sub-problems was actually first developed in operations research in order to solve various optimization problems, and this came from the middle of the 1900s. And the term dynamic programming was actually coined by Richard Bellman in the 1940s. And the thing to note is, of course, that the term programming and dynamic programming has nothing to do with computer programming, because this was well before computer programming was actually a common thing. Computers were just beginning to be invented around this time. And what he meant by dynamic programming initially was some kind of clever step-by-step way to solve a problem without fixing the strategy in advance. So it is not a static strategy, but a dynamic strategy. By around the 1950s, the current notion of dynamic programming as a recursive strategy of solving smaller subproblems, but in a well-organized way to make the problems manageable in number, which is pretty much what we do in algorithms today. So this terminology became fixed around 1950s, although the original terminology of Richard Bellman actually was talking about something slightly different. But this is only historical. Right now, what we have discussed in this introduction is what algorithm design people mean by dynamic programming. A recursive formulation in which subtasks are well organized to be minimum in number, and they are solved efficiently so that you never solve the same subtask twice.